questions from yesterday? Everything was clear? All right, great. So, and we're going to continue where we left yesterday with the MNIST data set. And one thing that we discussed briefly was taking an image 28 by 28, which is, by the way, a very toy example, right? In reality, you will never have 28 by 28 for computer vision tasks, unless it's something very specific application that you may end up with very little images. But again, MNIST dataset is like a toy dataset, benchmark dataset that is used for other tasks. But one thing that we said that we have the image, and the first thing we do is, apart from pre-processing, which is dividing by 255, is actually taking all the pixels and just flatten them, making them a vector, right? Okay, so, and then we said that each of the pixels will serve as one of the features. So at the end of the day, the input will have 28 times 28, 700 blah. Okay, each of them will be one feature. What do we miss from that? We said yesterday that we are missing the information from our neighbors. We don't really know how the pixels connect to each other. And when I say connect, I mean how they relate to each other, because there is no connection. I mean, we are not talking about graph theory where everything is connected. But we don't even know how they relate. Okay? Now, if this is the motivation for convolutional neural networks, the CNNs, we want to actually take into account spatial information. Okay? This relationship between pixels, it's called spatial information. If you, parenthesis, if you want to include time into account, then we call it temporal information. But that's not the case here. We only want to take care of the spatial information. So, CNNs are perfect for this task. Okay, and this is actually how they start. In the first slide here, the introductory, this is what we are actually seeing. Most likely your input data will be an image, okay, or a video, which is a sequence of images. And you see here that within this image there is like a little box that we are creating for a particular neighborhood in that image. This is what we're going to see later on called the kernel, okay, or the filter. And this is the beginning of the CNN. This is how we're going to extract features eventually. Okay, we're going to have a filter sliding across the input image and extracting useful information. Okay, and this useful information could be, you could imagine, edges, corners, if you have medical data, particular pieces of a tumor, cancerous tumors, and so on. And one more thing, again, we talked about the main motivation, but one more thing that we also briefly mentioned yesterday was the explosion of dimensionality. And again, this is going to lead to something called the curse of dimensionality, which eventually will lead to overfitting and so on. But before we even go to that, you can intuitively think that, okay, let's say, again, reality, you have to work with greater than 28. So let's say that we have 256 by 256 input image, just one channel, grayscale. If you flatten it, you're going to create 65,000 input dimensions, features. What's going to happen if you're going to get to the next layer with 1,000 neurons? That is going to take you to 65 million parameters just within the next layer. And imagine now we have more layers, and eventually we're going to do classification. But just within the next layer, you're going to generate 65 millions of parameters. That's too much, right, to train. And again, there is no need. First of all, even if this is going to be powerful, this is going to be too slow, and plus you will never get this this spatial information into account. You will never get useful features out of it. Any questions here? Okay. The integrated feature learning is actually at the heart of the CNN. So the convolutional approach, and we will see pretty soon, we have two stages in the network. One is actually the feature extraction, where you are getting all of this useful information from the images, edges, corners, again, health, medical pieces of information, and so on. And at the very end, the second stage of the network is actually when you do classification. This is when you are actually flattening eventually. I mean, at the end of the day, you have to flatten all of your input features, all right? And from there, you do classification. So remember, the key takeaway from this is that there are two stages. One stage is the feature extraction along with the input data, and the next stage is the classification. This happens simultaneously, okay? While we are doing training. But we can see it as two stages because later on, the two stages will be very useful for you for other tasks. And I can make, before I go to the slide, I can make a small parenthesis here because I think this is useful. Have you ever thought someone asking you, okay, you are doing classification using CNNs. Perhaps you have used CNNs, okay, like a black box. Because it's very simple. In TensorFlow, it's just one line of code to use CNNs, right? Perhaps you have used. But the main question is, how do you know what are the most important features for your classification? How do you know whether there is a pattern in clustering of your input data? Now, CNNs are very useful for questions like this. Why is that? Because every time, anytime, after you have trained your network, you can go to any of the layers, okay, and inspect the extracted features and see how the data look like, or whether the data cluster in a particular fashion within the space spanned by those features. Does it make sense? I'm going to change the wording a little bit here. The edges, or the corners, or all the features that the CNN is extracting for each layer, they are actually dimensions, numbers, right? And what we actually have achieved is a dimensionality reduction at each layer. Okay? And what can we do when we are actually achieving dimensionality reduction? We can take the principal dimensions, okay, and project the data onto that dimensions. Okay? And now we actually have something great because we can see how the data are organized in a lower dimensional space, in a space spanned by particular features. Okay? Keep this in mind. If you don't get it, that's fine, save it, okay? Because that will come up anyway, okay? For now, probably something that rings the bell is principal component analysis. Many people have actually used it. It's when you have data and you'd like to extract two components or principal components from your data, and then project your data onto those components and see how your data look like in a low dimensional space, right? Same thing can happen with CNNs, by the way. All right, what is actually the key aspect in CNNs? It's the convolution. And this is what differentiates you from a traditional neural network. What is this mathematically? Nothing but a sliding window, a convolution. Mathematically, we do not have the equation here, but it's like a huge integral, blah, 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 with many things inside. But it's nothing but a window, as you can see there. You have a function, f of x, and what you are doing, you are taking actually this window and you slide it over that function. And then the result from that will be the result of your convolution. That is what you're going to extract. So whatever is inside this orange box with the blue line here will be the result of your convolution. Will be the result what you're going to take to the next layer. And actually, this is what you're gonna use in order to train your network. The result from these two objects. Okay? And when I say sliding, later on we're gonna see that it's sliding, nothing but moving from pixel to pixel, okay? And taking one filter, one box, place it on the image, and just take it to the right pixel by pixel. Okay? Now, mathematically, again, we do not have the equation right now. There are two different ways of thinking when you are using convolutions. Again, this is a parenthesis. One is actually the continuous way, which is an integral of something. If you do neural networks, you don't see that. And then there is actually the discrete way, which is what we are doing here. It's pixel by pixel, and it's actually nothing but a summation of multiplications. That's all. Okay, and that is actually what is happening. The filter is my kernel, is this box. The bottom part is actually the image, okay? And what we do is that we just take this box and place it on the top of this image. And you see how nicely each of the little sub-boxes align with the pixels of the image. Okay? So basically, the way you have to think it is that the image has those little boxes, which is actually nothing but the pixels itself, right? Now you take each pixel, you map it to the corresponding filter pixel, you multiply them, and then you move to the next piece. You do the same, you multiply, and the two products are added together. And you do this for all the pixels with the corresponding pixel filters. Okay? Again, we're going to see the equation, but that's what we do. That's nothing but this simple operation. Okay? Question? No?
I just finished calculus too, so.
Well, what did you finish?
I just finished giving the example calculus too.
Ah, okay. Oh, okay. So you are familiar with it. Very good. Very good.
I was just thinking of they're all primitives.
Uh-huh.
Each one of them can be considered a primitive that has to be added.
Yeah. Yes.
I was. How does this connect to the yesterday neural networks? Are you describing a neural network here?
Very good. So the question is, how do we relate what we are talking here with yesterday, right? And these are two different types of architectures. So these are distinct. However, now yesterday we talked about neurons. Here we do not have neurons anymore. What we have are the kernels. Okay? And what we learn are actually the weights, which are nothing but those entities within the filter. So you are learning nothing but, each layer will learn nothing but a lot of filters, or many filters. Good? So this is the distinction between yesterday and today. We are moving away from the traditional neurons, which are these little circles, okay? And now we are talking about filters like this, and each filter will have nothing but weights at each position. So here we have 3 by 3, 9. So we are talking about 9 weights. Okay?
Practically, as I suppose, what I was saying is that yesterday we were training only data, fed data. Today we are interested about another feature.
A different type of feature.
Yes.
Yes.
And this architecture needs to make this thing.
Exactly.
And also, because the data are very, very extremely high, lot of data, we separated the phase of training in different places of the pixels.
Exactly.
Places that are shaping in different stage, different shapes.
Mm-hmm.
And at the end, we create all the patterns.
At the end, we create different patterns from the image, different aspects from the image.
Different. Yes. This is
Excellent.
practically.
Yeah, that's all. That's the story. Okay. and again, the one thing that I'm going to add to this is that there is no need to flatten anymore at the beginning. So you just take the 28 by 28, 256 by 256, you give it to the network. And then the network, the first thing that it will do, it takes one filter with weights that's going to be trained eventually, place it on the image, and now start doing this sliding. Okay? And again, we haven't seen the equation of the result from the image and the filter and the sliding, but we're going to see it pretty soon. Okay? This is the one. The left is just a small piece of the image. So remember, you have a 256 by 256. Okay, but just look at the upper left corner of the image and isolate 9 pixels, 3 by 3. Okay? Now take a filter, the purple one. Remember, the filter has weights that's going to be trained eventually in the network. What we do is just we take this one and place it on the top of the upper left corner of the image. Okay? And do this very simple thing. Take W0 multiplied by X sub 0 plus W1 times X1 plus W2 times X2 plus W3 times X3 plus dot 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 W8 times X8. Done? Okay. You have a very long equation now, which is adding these products, right? Now, what we need is the nonlinearity to be included. This is where we're going to add the ReLU on that. And we are getting what? A single number. Remember, the ReLU is the max of two numbers.
Yes.
0, comma, blah. And what you are receiving back is just a number, Z0. Yes? Okay, save this number because now we are taking this filter and we slide it to the right of the image by 1 pixel. Yes? Take this filter, place it now on the image, but slide it just 1 pixel to the right. So now this W1 will be multiplied by X1 plus W1, W0 times X1, W1 times X2, W2 times X3. It's not there, but I assume that it is, right? W3 times X4, and so on. Add it, ReLU, you get another number, Z1. Okay? Slide it one more time to the right. One more time, go down to the left. Right, go down to the left. Right. We are done with sliding this filter at the whole image. What do we get? Bunch of numbers. Z0, Z1, Z2, Z5, Z9. Okay? What do we do with those numbers? Those numbers will be placed in a two-dimensional array. And this is what we call your featured map. These are your new features. This is a new way of looking at the image. And it's going to highlight, you will be able to visualize actually. You're going to highlight a particular aspect from the original image. If you are talking about cats, you may actually see highlighted like the ears of the cat and nothing else. Now we are talking more, this is just one filter, right? Imagine now that we can use 32 filters and do this process 32 times within a layer. So imagine how many feature maps we can extract from a particular image. All different aspects of the image. Now we have another layer with the same thing. But now, the thing is, and we will see soon, the thing is that we do not apply those new filters to the input image anymore. Because we move to the other filter, to the other layer. And the input of the other layer is just those feature maps coming from the Z's. Z0, Z1, blah, blah, blah. So the new filters will be applied on those feature maps. Do you see the evolution? And we're going to extract new aspects from the image. We will see that pretty soon, but it's good to just imagine it without seeing it. Yes. And you have another. Let's start and then we go. Yes.
So for all the filters, are there going to be more parameters, or the parameters are going to get compressed?
They're gonna get compressed. So the original pixels over there, they're gonna get compressed. I mean, we still have a lot of parameters, right? The parameters are nothing but the weights of the filters that's gonna be trained. But they're gonna be compressed. There is a step that we haven't actually talked yet, is the downsampling, which is necessary. But you will see. Good point. Yes.
I have a question for the numbers.
Mm.
We get as many numbers as pixels are?
No. As filter. We are not getting the z's are not the same as the x in terms of one. Yeah. Otherwise, because if they are the same, then we will not go any dimensional regression, right? So imagine that think it this way. Imagine from a neighborhood in the image of 9 by 9. So this is a 256 by 256, but I'm just looking at a 9 by 9. Okay, and I have this filter. So imagine that the result from these two is just a single number. Okay, and then sliding to the right, and then applying this filter again to this result is another number. Yeah. So the size of this matrix that contains the z's will be much less than the 256 by 256.
And when we slide, there is also overlapping. That is
When we slide, there is overlapping. There is something that we can avoid the overlapping if we want, but this is a parameter eventually we're going to discover. Other questions? Okay, here we are. This is the sliding that I was describing. You see the filter applied on the top of the image. The left light blue is the image, the pixels. The blue box is the initial filter, and then we just slide it on the right, and then there is what Ogerta said, the overlap, right? Because some of the pixels will be seen by the filter multiple times. However, keep in mind, because we're going to discuss this soon, that some of the pixels will actually meet the filter just once. You see which one? This. This pixel will meet with this filter while it is sliding just once.
Can you explain the loss vortex?
Yeah, I had it in the next slide, but I'm going to explain it also now. Thank you. So this is important. Why? So imagine that you are working, let's say, with health data. Okay? And there is the health data, for example, MRI images, fMRI, and so on. They are most likely like black and white, right? Grayscale. I mean, they're not gray, they have more chance, but what you see is like grayscale, black and white. And when we do, let's say, an MRI, it's great when you would like to detect particular tumors in specific organs in your body. So while you are taking this MRI, you generate a lot of images. The tumor could be actually be located here, at the corner of an image, and everything else will be black. It's the way how the scanner works, right? When you go inside the scanner for the MRI and you capture the body, it may be somewhere here. Or here is an organ, and this is actually the abnormality. Okay, what happens if this filter meets with this pixel just once? That means that we miss the tumor. Remember, at the end of the day, we are doing detection. We are doing classification. Does this image include a tumor, yes or no? They give no because this didn't capture enough of information about this pixel here on the very top left, which the tumor is located. Okay? So this is actually really important to notice right now, but there is a solution that is coming up. How are we going to fix that? Okay? Now, the the sliding, by the way, has, I mean, I wanted to also say that there is a terminology which we have to be fluent, okay? Because when you go to interviews and so on, they may ask you, okay, overlapping or sliding. They may not say the word sliding. They may say stride. Okay, it's a parameter that you actually set up. Stride means how much you move. One by 1 pixel, by 2 pixels, by 3 pixels, and so on. Okay? Right away, you can now connect with yesterday's discussion and think about whether it makes sense to move pixel by pixel, or 3 pixels by 3 pixels, or 5 pixels by 5 pixels. Remember, the sliding can happen pixel by pixel, or you skip 2 pixels and then slide. Okay? What happens if I slide pixel by pixel? I generate more parameters, right? More z's. Yeah. But if I do every 5, I generate less. Okay. When do I really need to go pixel by pixel versus every 5? I mean, again, at the end of the day, it's a parameter that you have to tune. But intuitively, when you have an application, you have to react on this. Should I go pixel by pixel, or should I go 10 pixels by 10 pixels? Yes. Very good. Very good. Excellent. So when the image has a high resolution, the one that we are using our phones, right? And this says, I don't remember now how many megapixels. Yeah, whatever it is, the iPhone. Okay? So you take a picture, and you now want to slide. Okay, so the pixels are very close to each other. So if you just move from one pixel to the other, do you gain any type of information? No. Most likely the probability that the information that pixel A and the next to it, pixel B, is the same. Okay? When you just capture, let's say, landscapes. So the probability that one pixel versus the next pixel, the green grass, it's actually the same, right? So there's no need. So actually you can move away. However, if you are working with particular applications, I didn't mention landscape randomly, okay? There is a very particular application. There is now the military application, right? So you are trying to detect the drone. The drone is on the air, is in the sky. The sky is blue, right? So the drone will look small within the blue sky. So you need probably every pixel if you're gonna use CNNs for that. Okay? So depends on your application. And again, you do also hyperparameter tuning, right? You have training data for that reason. All right? This is actually the solution of what Ogerta mentioned, the upper left corner. So this is the original image, right? The 256 by 256. And remember I said I can place a 3x3 filter on it and slide it by 1 unit. And then if I do, and the tumor is located here, the filter will meet with this pixel just once. Okay? Can I get rid of that? Of this issue? Yes. What do? I take the original image before, this is the pre-processing. I take the original image and I pad it with zeros around. So now, what's going to happen? If you place the filter now, the 3x3 here, this first pixel will meet with the filter multiple times, because then you slide it to the right, it's going to be one more time that it's going to see the filter. Slide it one more time, maybe one more time, okay? So 3 times versus 1. Therefore, more chance to detect something abnormal on the very left up of the image. Good? Questions?
Should we fix this, or it depends on what we use it for?
Depends, yes, this is actually also application driven. So depends on what you are working on. You may have, for instance, one very common application that you have to do this is when you are working with NLP data. NLP data means you have documents, right? Document length is different. One of the requirements should be that each input data point should have the same length. So you are actually padding with zeros the documents that have less characters than the maximum. Okay, or you identify, let's say, maximum number of document tokens, words, 512, and then you say, okay, I have, for those documents that have less than 512 tokens, words, I need to pad with zeros. Does this affect the training, the zeros? No.
So when we add the padding, it means that we are giving some like artificial information for the neighbors for the age.
Exactly. Exactly. We need some, we give, you said artificial, very good. It's the simulate a little bit more of space, so one of the pixels will have more interaction. Okay, now yes, you have a question for the previous one?
Yeah, for padding. So does it mean
For padding, yeah.
if we add padding, does it not mean that we use more tokens? Like for example, the example that you gave, in words documents, doesn't that increase the computer usage? Increasing the tokens?
No, we are not actually increasing the number of tokens. I mean, it's zeros, right? So remember what the final operation is. Multiply the filters by zeros, and then you are taking the max of the result. So at the end of the day, just multiplying numbers by zeros does nothing to this internal operation. It doesn't increase anything. And also it doesn't increase the input data. I mean, there is no, we do not increase complexity. Yeah. Again, remember, the parameters are located not in the input data, but are located in the window, right? In the filter or kernel. So this is where the parameters are located. These are fixed. We want 3 by 3 and 32 of those guys. And then the input data is what it is. 256 by 256. If you want a padding, doesn't increase any complexity. Okay, and you again? Yes, sorry. Yes.
I want to ask, does the size of the slide window determine how much padding we're going to use for viewing?
So you mean if, for example, we decide to have a 3 by 3, yes. Again, it's application driven, depends on your application, but it's somehow related as well. So, okay, application driven I mentioned. So for example, in NLP, remember I said previously we have documents, right? And documents contain words. And some documents have less words than other documents. But there, it doesn't have to do with the sliding window, with the filter. It has to do with the maximum number of tokens per document that you wish to have. So if you want to have 512 words for each document, and some of the documents have less words, then no matter what, you have to add zeros to reach 512. Okay? For all documents in your input data. Because all of them need to have the same length. Okay? We discussed compression. Okay? So remember, when we are applying this filter on that image, and we extract the z sub 0, z sub 1, and then we add it to a matrix, right? Or not add it, place it into a matrix in a two-dimensional array, that's the result. This is a feature map that we are generating. Okay, so this is probably for the network too much of information. This actually can increase the number of parameters. Now, do we really need that much of information to move on to the next layer? No, the next layer doesn't really need a feature map that is very rich in details. It needs something more compressed. It needs something that still maintains a lot of information, useful information, but gets rid of the fine details of an image. That is the reason why, in addition to what we just did, we are adding one step that is called, before we move to the next layer, one step that is called downsampling. We are just reducing the number of pixels from each feature map before we move to the next layer. And how do we do that? If we decide that the downsampling needs to be 2, or we want to get a 4x4 new feature map, you have on the left the feature map generated all the z's, z0, z1, z2, z3, z4, z5, z6, blah, blah, blah. Yeah? So if we decide to reduce this dimension, one thing we can do is actually look at a particular neighborhood of that feature map. So that's why you see 3 different colors here. Okay? So on the very top left, one thing you can do is actually pick the maximum number of this. 1, 1, 5, 6, the maximum is 6. The next neighborhood is 2, 4, 7, 8, you pick 8, and so on and so forth. Okay? This is called max pooling. You are pooling the maximum number from each neighborhood. Is this sufficient for information transfer? Yes. So the major pixel, okay, will be represented in that new feature map. So if you, again, you have a landscape, right? And there is a drone. There is gonna be like, in the drone, the pixel of the drone, it's gonna be like a different than the neighbors. So just pull the maximum number and place it into a new feature map. You still get the useful part of this image. There is one more thing you can do. Instead of max pooling, you can average. This is another operation. So averaging means that you are taking all of those numbers in that neighborhood and you add them together and you divide by 4, right? 1 plus 1 plus 5 plus 6, divide by 4, get the number. Same thing for the different neighborhood. So both are what we are using for downsampling. Now, whether you use max pooling or averaging depends on the application. It's a parameter at the end of the day which you have to decide. You as a user. Okay? Questions here? That, so, and I'm coming to you. That is coming actually, this is going to be the input to the new layer, to the next layer. All right? Yes, another question.
Just a small thing. We can take also why not the minimum? Can we take the minimum? Does it make sense in some application?
I don't know. Could be. I don't know. I haven't thought about it. I mean, if there is a major difference, so what you're gonna produce at the end of the day if you take the minimum or the maximum? It's because the minimum is also the negative of the maximum, right?
If you are trying to find something light in a dark background,
Yeah.
maybe this works better.
Yeah, maybe that works. I mean, at the end of the day, it's where you represent black and where you represent white, right? So if you say that black is the maximum and right, it's the same. It would be the same. You have a question, please?
No, I was
Oh.
just thinking about this.
Okay. Other questions?
I'm sorry, why do we do downsampling?
Very good. So we do downsampling to reduce the complexity. Remember, each layer now, if this is the result of the layer, that is still too complex. I mean, at the end of the day, it can handle it. The network can handle it. But you're going to produce more parameters rather than doing downsampling. And we do downsampling simply because we can guarantee that the useful information is not lost while we are doing downsampling. The network still sees the important aspects, and at the same time, we are reducing the complexity of the model. Okay, this slide just shows to you that we have more than one feature map. We can generate more than this, all right? Here we are. Each feature map could be of any, can represent different aspects. That's all that it says. We already discussed this, so we are good. And remember I said CNNs have 2 stages. So one stage is the feature extraction. It's when you are extracting those feature maps. And you see you start with an image of the digit number 3. Here we have 32 by 32. You do convolutions with 1, 2, 3, 4, 5 filters. So you generate 5 feature maps. You do downsampling. Oh, I call it also, some people call it also subsampling. But for us, let's call it downsampling, okay? You do downsampling, and then you go to the next layer. So convolutions, subsampling, and then it's when stage 2 happens. Within the same network, we need to do at the end to do classification, if your end goal is classification. And what you do is you are taking all of those feature maps, each of them, and you make them vectors, and then you stack them on the top of each other. And you generate a very long vector here. And this actually takes you to the last layer, which you will do classification. Remember, at the end is softmax, where you actually have to predict or have to get predicted probability values. All right? And we will see from a practical point of view that the dimension of this here array may be too large. So we may want to actually reduce it by doing something else. We'll discuss this. This is the same thing of what I just discussed. I'm going to skip it. And this is actually a very nice visualization. So input image is the digit number 7. First layer is a different aspect of the digit number 7. After you apply your filters on that, you're generating different feature map, different representations of the digit number 7. Then you are doing pooling, okay, downsampling. You are actually compressing the dimension, but you still see that there is a digit number 7 there, right? But in a lower resolution, which is fine, which is actually good for the network. I mean, not good for our eyes, but good for the network. And then there is another one, from here to there, you are doing again again filters applied to those. You're generating again different aspects, and so on and so forth, until you go to the output layer, which is just predicting probabilities of the digit number 7. So you see that here, at this stage and there, these are actually aspects or feature maps that our brain or our eyes cannot actually recognize that this is a 7, right? However, our brain can. Convolutions know that this is 7, all right? And this works very, I don't want to say, I'm not a neuroscientist, but I can say that the way our vision works and the way we capture objects in a room is something very similar to this. Okay? So our brain has different layers of processing this information. And that's why you have noticed perhaps that if I see someone, I can actually extract particular features of their face, and I can recognize this person after 10 years. Because particular aspects do not change after 10 years of our life. Though I'm getting older, but something on my face doesn't change as much. So that's why our brain can recognize us. Okay? Yes?
Do you first the pooling and then the convolutional, or it doesn't matter?
No, first convolution, then pooling.
Because here in this slide you read, I see.
Convolution.
So it's convolution,
then
pooling, convolution number 2,
okay.
pooling.
Well, it's from top, from bottom.
Conv is convolution.
Bottom to top.
Bottom to top. Sorry, I was reading the other way.
Okay. Why CNNs? And this is the last slide. Yes, this is the last slide. We said key takeaways, parameters, reducing the complexity. Is translation invariant? Very important. I think this is one of the quizzes too. It recognizes objects regardless of their position in the frame. I can actually get something, an object, rotate it, and we are good. Spatial hierarchy mimics natural vision by building complex objects from simple edges. So this is you already saw with the digit number 7, that we extracted feature maps that do not look like 7, but the network knows that this is 7. Okay? And data efficiency, of course, since we're talking about less parameters, we can use also less data to train. Good? Excellent. I think that's all from that. Any questions before we go to the next set? So again, the idea is the same. We will go through the slides, then we have a break, then we have a quiz, and then we go do coding.
How do we do the training? Do we have a loss function here? What is the loss function? How do we do the training?
The loss function, so that's a great point. Remember yesterday we talked about backpropagation? Yeah, so this is actually how we train the model, the parameters. The training here is again backpropagation. Same thing, gradient descent, pick your optimizer and so on. The training loss is again the same as yesterday. If you do classification, you are using the same loss as you used yesterday. Okay? Now, instead of just learning parameters, weights that are linking neurons from one layer to another, now you are learning what? The weights that are located within the filters. It's a different way of thinking where to place the weights. Okay, but the training is exactly the same as yesterday. Backpropagation. Okay? Good.
So I continue with the second part, which I think is a bit more practical, let's say, because there will be a simple architecture, a convolutional neural network, where we are going to have some layers, and I'm explaining details, and maybe it will be a bit clear about how convolutional neural network works and so on, based on what was explained. So as you see, the title here is about small code and massive vision. What does that mean? So you'll see that we'll have only maybe 10 lines of code written in Python, in here, but what we can get is like a great output in terms of the accuracy of that image or digit recognitions and so on, only with this a few lines of code. When I say few lines of code, it means also a simple architecture in terms of the number of layers that we have and so on. If you see here, we have highlighted two different layers, and this will be the main components that we'll talk about in convolutional neural networks, which is the first one is the convolutional, Conv2D, and the other one is about max pooling and so on. So we don't want to treat it as black boxes without understanding what happens, because if you have the data set from yesterday, if you just copy and paste these 10 lines of code in Python and run it, you'll get the output, you'll get the accuracy of training that it will be around 98%, and the final accuracy for the testing end up to 91. Let's say it's from 98 to 91, but the idea is to understand and to open this black box and to see what happens in between these layers. So what we get from one layer as output, that will be an input going to the next layer and so on. And we bring here a simple version because you can make it more complex with adding more layers and so on. So let's think about the data that you have, the data set. Still the same data set that you used yesterday. What we have some raw data, some raw images. They are in grayscale, okay, grayscale. And this is the raw data that you have. In total, what we have? We are going now, you see the first two lines of code in here. We have not started to build any neural network at all, no convolutional, no CNN at all. We need just to have to prepare the data, to load the data that we need. How we are loading in the same way using the load data method that you used yesterday, and if you run this method, the load method, it's going to come up with 4 different data sets. So in total, we are having 4 different data sets. The first one is the train images, the train labels, the test images, and test labels. In total, we have 70,000 images, okay, and 60,000 images are used for training, so they belong to the train image and train labels. I'm talking about the shape of that data set now. And in terms of the tests, so we have 10,000 that we use for testing. So in total, there are 70,000 images, split it 60,000 for training. You need to train to learn. And when we say training and learning, we need to figure out the final weight, so this is the process of learning. And it's also important to understand, because we are talking about 2 different types of layers in here, convolutional and max pool, and you have to understand which of these layers is doing training and which is not learning or doing training. We don't have parameters at all. This is what we'll cover. now. So, and after that, what happens? You see on the right side of the image, there is the concept of the tensor, and the tensor itself is like a way of shaping the data in a tensor. What does that mean? It's about how we want to organize the data, because in order to feed in the data into the first convolutional layer, so they have to follow up with a structure. And this is what we need to do it using the sensor. So the shape of the sensor it will be 28 pixels by 28 pixels, and that one dimension here. What does that mean? It's like we are dealing with images, grayscale, so the channel is 1. If we are going to have red, blue, green images, so color images, that channel should be 3 rather than having 1. But we bring here a simple version with grayscale images that we are processing, and now the shape it will be of the tensor, it will be 28, 28, and 1. So these are the dimensions. Now let's have a look now to the code, and in the next slide we are going to understand line by line what all these layers do. So in the first one, we need to shape it, because this is the input. So the input that we want to shape, it will be with the dimension 28, 28, and 1. We are not specifying here the total size of the batch, and you'll see the output in the next slides that it comes as none, because the neural network can process any batches of images that you have. In this example, there will be 60,000 that we are using for the training purpose and so on. So where it comes now? So inputs now is, what is inputs for you? I'm talking from computer programming, let's say, point of view. What is inputs here?
Something that
Is it an object?
Something input would be something that the user will give, or something that gives the
Is it a variable?
Yeah.
At the end of the day, it's a variable. Okay? Now what happens? The second line of code, x equal to layers.com to b, and we have specified
The first line, I'm
parameters
sorry.
in here.
The
Filters.
first line of code, what does the first line of code do?
Here, that one.
Yes, yes.
So it's just doing the shape. So it's just shaping it in a way. So what we have one channel for the gray scale images, and we have the pixels 28, 28, and 1, and it's just shaping with the tensor, sorry.
It is
Yeah.
making.
The tensor.
What is the input and what is the output?
So it's just the shaping what we have. Now it's shaping it.
But the
Yes, it's just shaping it, because this is the input that it will go to the next, to the first layer. So the first layer you see here is the convolutional one. And we have some parameters about the filters, the kernel size that I explained also, and also the activation function that it will be the radio now in the first one. And what it takes, look here, it's taking that input as a parameter. The first input, it goes to the second one.
I think this question is most what's the input
So we are
exactly, but
shaping
it can be different
in
things.
the
It
tensors,
depends on
and
what
after
you want
that
to
we are
input.
using, because if you don't do it and if you don't shape it
Tell me one
with
more
these 3
time.
dimensions,
Yeah.
you
This is the
cannot
input?
fit that data
Can
into
be
the first
anything
layer,
you
which
want
is
to
the
work with.
convolution.
This is like an
Okay?
image, one image.
So now what
28 by
happens? Here you
28.
see that we have specified the filters
There's a
equal to
specific-
32. And it will be a question about why 32
This
in this example.
keras
Okay?
dot
So
input
why
is
not
a
40?
Python
Why not
command.
50?
Yes,
Why
it's
32?
syntax. It's syntax
It's like,
from the
a
keras.
standard, let's say. Usually we start with the numbers power 2
When we are
because
loading
of
it,
the
we are loading keras and page of
computational power
flow.
of
So this is
loading.
just syntax.
See, 32
Syntax,
you will
yes.
see the next one it will be 64,
What
the
does-
other
what is the output?
128. But
what is the
what
purpose
I
of
want to
this?
explain here
This
is
is
the
just
fact
the
that why
inputs
we
for the
increase
network.
it. So first, in the first
for the network.
convolutional
Yeah,
layer,
an image.
we want to
An
capture
image.
the
It's
basic
a matrix.
features
It's
or
a
the
matrix.
basic
It's a
patterns that
matrix.
it exists in the images.
Ah.
So it can be
It's an
some
empty
edges
matrix
that
at
we
the
want
beginning,
to,
some sort
to
of
figure out
variable.
in the first
It's
layer.
an empty
When we
matrix
go
at
to
the
the
beginning.
second convolutional layer, you see that now the
And
figure
that
becomes
goes to the next- to the
64,
first layer.
and after that becomes 128. Because for the, what is the reason? The first reason is that we want to figure out more complex patterns, but also is due to the fact that you see, when it comes to the first convolutional layer, the input it will be the data that you have that you reshape. Okay? When it comes to the other one here, convolutional 2D, this layer here, the input it will not be any more the raw data that you have, but the input it will be what is coming from the previous layer. Okay? So now this is patterns that you have identified in the previous layer, and they become the input in that specific layer in order to process them in a way that you can identify more complex layers. So that is important to understand why we are moving from 32 to 64 and to 128. This is the concept behind what I was explaining. So what we do in here, we are going to grow in depth. And how do we grow in depth? We grow in depth by increasing the number of filters, and the first one is 32, and we go to 64, and after that we'll end up with 128. And we want to shrink in the spatial size. How we shrink it? This is the second layer that we are doing for shrinking, and this is the max pooling. So what happens now? The first layer is the convolutional one. So we have 32 filters, and the window now, the kernel size, it will be 3. I didn't specify the other parameter because there is the height and width. If it's 3, it means that it will be a square, 3 by 3. But if you want, you can also put a comma 4, and it will be a rectangle, 3 to 4. Usually in practice, we prefer to go with squares, okay? And it doesn't mean that it always has to be 3. You can go for 5 and so on, make it bigger, smaller. You can also test and so on, okay? So the size it will be 3. The activation function is the ReLU. So what does the ReLU? It's going to transform all what we explained yesterday when we sum all the way through the input, and it's going to transform it using the rule of getting 0 for negative values or the maximum value that we get. And you'll end up having a single value from the ReLU one that is doing the transformation, and this is where the activation function works now. So, if I go, I think in the slides here, what happens? The input now, it will be 28 and 28, by 28, yeah? Because these are the pixels. When it comes, it's something important to understand that even the convolutional one is going to do a slight shrink, not a dramatic one, like the max pool. The max pool is doing a dramatically shrink in the size. But even the convolutional one is doing some shrink. Why? Do you have an idea? Because we discuss and we explain it. Why do we have this shrink? And with the shrink, what does that mean? So the dimensions at the beginning in the input in the data that we have, the dimensions are 28 by 28. When we do the first convolutional layer, now what happens? The dimension will change, and we are moving from 28 by 28 to 26 by 26. Do you have an idea why the dimension? Yeah.
Because the number of filters scanning are, if you get that times n as an input, n minus 2 times n minus 2 is 3 by 3 is the dimension of the filter.
Any other idea? Do you something in orange in here?
Because we have a 3 by 3 window.
So we have the loss border that we explained in here. Okay? The loss border. No, it's not 0. The loss border itself.
Once or twice.
Yeah.
The
Border. Yeah.
Because we have a 3 by 3 window, and we can fit this window 26 times. If we slide it one by one, we can fit it 26 times in a row.
What?
Just
Yes.
counting.
Why?
Just a minute.
There is a border between. And how it works mathematically, there's a formula. It will be the size of the dimension that we have, minus what? Minus the kernel size. If I go back here, the kernel size is 3 plus 1. And it comes 28 minus 3 plus 1 because of the border loss. It will end up with 26. So there is a shrink now. But it's not so important, let's say, that kind of shrink. But something that you have to understand is about how the output has shaped now in terms of the dimension. So in the first, now what we are having, that none means that it depends on the batch of the data, of the size of the data set that you have. It can be 60,000 in this example. So now the feature map that we have, this is the output that we get from the convolutional one. It will be 26 by 26, and now 32. So the channel, let's say, has changed. Raw data, the channel was 1, yeah? Now, in the feature map, the channel has changed to 32 due to filters that we apply. So it's equal to the number of filters. This is the output that we get from the feature map. So, saying that from the second box, is the output that we get from the first convolutional layer, from the first layer. So, this output now with 26 by 26 and 32 is going to be an input to the max pooling to be layer. Okay? But keep in mind that in this convolutional one, there was a process of learning, of training, of updating the weights and so on, of backpropagation that we talked last week. And that is important because in the next slide we are going to calculate some parameters about how many parameters we have in each of these layers. And there is an activation function and so on. If you look now to the other layer, which is the max pooling layer in here, we don't see any parameter in terms of the activation. Do you have any activation function in that max pooling one? No. We just specify the pool size 2, which still is a square, 2 by 2, let's say. Okay? And now in this layer, we are not doing any learning, any training and so on. It's just for shrinking. So the process that we are doing here is about going depth in terms of the filters, but also shrinking the spatial size. And shrinking happens, or is done, by max pooling. And that's why we consider it like the hero layer, let's say. And you will see why with some evidences in terms of the parameters and so on. So now what happens? Well, after this input now, the feature map goes as an input into the max pooling one, okay? And the pool size is 2 to 2. So we will end up now as the output that we get, it will be a pooled map, but the size will be half. So from 26, we'll end up to 13 now, okay? So we are increasing the depth, but we're shrinking the size from half of the size. So from 26 now, we'll end up with having a pooled map, or the output of this layer. It will have that kind of that specific dimensions. 13, 13, and 32, which is the channels. It has not changed. It's keeping the same as in the feature map is going to as input. Okay? So now we have shrink the spatial size. Is that clear what happens? Okay? So we are going depth in terms of the filters, but we are also shrinking using the layer of max pooling without having any training at all.
Why half? Does it always happen, or has to be half?
Why? Do you see something related to 2 multiplied by 2? There is no overlapping, okay? And that is why it goes to 13, okay?
Does it, or what's the difference if we have a different size of kernel? Let's say 3 by 4 or 4 by 4?
The dimension will change. You are having the different dimensions. But usually we recommend to have, as I mentioned, usually we recommend to go for squares. So I just specify here one, you see the kernel size equal to 3, but you can also play with the different in terms of the height and width. So you can also specify 3 and 4 and so on.
Yes, but I want to know the difference. What's the difference if you make less?
A different dimension?
Square by
Different
4,
dimension.
square by 4.
Different dimensions.
Yes.
It will be different dimensions that you have in the feature map, and different dimensions that will end up with the pooled map. So it's about the dimensions.
At the end of the day, it's complexity. Again, the determination of the kernel size is up to the user. It could be 3 by 3, 9 by 9.
It's a
depends
matrix.
again on the application, depends again on the hyperparameter tuning that we are doing. It's like the number of units, how we select the number of units. So having more means that we increase the complexity of the
It's basically a matrix, right?
Because if you have
It's a
3 by
matrix.
3, you
Yeah.
have 9 weights, 9 neurons in your mind. Okay? If you make it 3 to 4, you will have 12 weights. Okay?
Sorry. Below the boxes you write the output none. What does
It's
that
the
mean?
total number of images that you have. It depends on the total of images that you have. In this case, it will be 60,000. Okay, we didn't specify it. It's none because the network itself can handle any size for the page. Okay.
You don't need to.
And again, this is sample code,
Yeah.
so do not worry to capture every
It's okay,
detail. This probably doesn't run if you
If you try
already
it.
done. But not worry to capture everything.
You're
Also,
not gonna need it.
when you are working with Python, sorry, okay, this one. When you're working with Python, nowadays do not try to do character by character code. Okay, computer scientists may disagree with me, but syntax is changing all the time. So TensorFlow can be updated next year, and you won't see this output anymore. Okay, so do not take it by heart, and do not get feelings with the code. So this is more about syntax. But you understand the complexity is the important.
Yes, okay,
Yeah, that's all you have to keep in mind, the complexity. Now, when you use 9 versus 3, it's hyperparameter that you have to tune. So you have to try different numbers and see which number will give you the best performance for your training.
You can play with all these parameters and see how the performance might change. So what is important now to understand how this neural network works. So we had a convolutional and a max pooling layer, okay? So it's clear what we did. So we included 32 filters in the convolutional, and after that we shrink it using the max pooling, okay? So now what we are doing, we are repeating now. There is a repetition, let's say. So we apply again. So now the output that we had from that max pooling now, that 11, 11, 32, that map that we have, is going to be an input now to what? To another convolutional, but what is doing that convolutional now? It's adding more filters. So it will be now the number of filters, it will be 64. So this means that we are going depth now. And what we do next? After that, we still want to shrink again the size from 11 to 5. Okay? And how we can do it? We do it using the max pooling now, and we keep the same. The full size it will be equal to 2. So we are repeating that process now, but what we are doing? Now we are repeating the process, but we are increasing the number of the filters. And the reason that we are going from 32 to 64 is because what happened? The input here in this convolutional layer, in the second convolutional layer, it will not be the raw data anymore. The input, it will be what we got from that max pooling, okay? So that map, it will be the input, and it captures some patterns. It's patterns itself, because in the first filter, in the first layer, that using the filter 32, the purpose of that, it was to capture some patterns. Now these patterns will be processed further, depth, with 64 filters, because we want to combine now these patterns in order to identify more complex patterns. And that's the reason that we increase the number of filters from 32 to 64 here. And we are, again, using the same activation function that it is the ReLU and so on. So in the next iteration now, what happens is that this is what we are having. So we had 13, and with a depth 32, that's the number of channels. And after that, going on with the convolutional plus the max pool, the second iteration now, we are applying another layer, which is a convolutional with 64 filters. And after that, the max pool, still with the same pool window 2 by 2. So what we are doing now, the data still are shrinked. Now the dimension from 13 by 13 goes to 5, okay? And now the depth has increased, because the number of filters is up to 64. Okay? That's all. So I'm not applying anymore any convolutional. There is one more that applying here. So up to here, this is what I'm explaining up to here. You know that the dimension up to here is 5, 5, and 64 due to the filters. Yeah.
I lost it. Sorry.
A filter is, because I don't get it, I don't understand. A filter is a 3 by 3 matrix with random weights?
No.
No, it is not. It is
When you
linear.
apply a filter, does it have some predefined weights?
And what is the filter? There are 32 filters. What is one of them, and are they related to each other?
Filters.
Yeah, I
It's
lost
a
it.
matrix.
Yeah. Data that we have. 64 now, we are increasing it, because we want to capture more complex relationship rather than using only 32 at the beginning. So
But
the first
what is one filter?
step?
Filter, I think,
Wait,
find the features. Find the features.
what is a filter?
Filter is a,
It is a data structure.
Mathematical function that for example, measure the distance from one
Here
point
it's
to one
made in my
point
slide.
to capture the details of the shape.
Okay, so plain mathematical, what
Yes.
a filter means.
Yes.
It's a 2 by 2 matrix
Okay.
of size 3 by 3.
Yes.
Yes.
With random.
Okay,
weights.
here, hold on this. So this is the architecture that we define. We haven't even compiled it, we haven't trained it. Alright, so once we train, the first step in the training process is that for each filter, we just give random weights, random numbers.
Okay.
Okay, second iteration happens, for the first second iteration of batch data gets in, the weights are updated.
Okay.
So the filters getting updated.
Now, 32 filters are unrelated to each other, or the
32.
second one is related to the first one, the third one is related to the second one, and so on.
No, they're not related.
They're independent.
Independent.
Independence, if you see the images,
Okay,
they
Yeah.
are independent.
So these are actually matrices that we say use 32 matrices
Okay.
and apply those matrices one by one to the input data point
And they
to
are
extract
independent of
features.
each other. Okay.
And
They are independent of each
they
other.
are independent of each other.
It was
But
clearly
they-
explained in an image.
For each image, they will produce 32 images.
No
For
image.
each,
For each image, they will produce 32 images.
yes, 32 images that do not include they include aspects of the original
Yeah,
image.
of course.
Yeah. And after that, we will continue with 64 and 128. So now here we are adding a new layer, which is the convolutional with filters 128, and we do not have after that layer, we do not add any max pooling, so we are not shrinking anymore. So what it will be the output before we go to the other one that we are going to flatten. So the output here. So this one, the last one, it will be the depth is the number of features, 128 matrices that we have, that we discussed. And now the dimension, it will be 3 to 3. Okay? So if I go back now, here, what we have to do? Before going to the last layer, because this is the classification. So we are up to here, we are doing feature extraction. And now we want to classify it. And how to classify it? In order to classify it, there is the last layer that is the dense layer. It's similar to the layer that we used yesterday. We explained yesterday the dense one. In total, we have 10 classes. The images has to be classified into 10 classes from 0 to 9. Okay? We are going to use the activation function softmax in here because we want to have probabilistic value from 0 to 1 in order to assign each output that we have to which class it belongs from 0 to 9, okay? But in order to do it, what we have to do? We have to transform or reshape the output that we get from the convolutional layer. So let's say we are doing a bit of the opposite that we did at the beginning. So now we need to change the output because we cannot pack that into the dense layer. And what we are doing? We are changing it using that flattened layer here. So we are adding a flattened layer. Based on the output that we get from this convolutional layer, the output what it was, 3 by 3 and 120, okay, filters, matrix. So now we want to reshape it. I'll show to you why we are reshaping in the vectors, okay, that's why we are flattening it. Now, all these different matrix that we have and values, we want to bring all of them in a matrix. So we are not changing the values at all. Whatever we received here, okay, for all the filters that we have, we are not changing it using the flattened layer, not processing, not training, nothing happens in here. It's just reshaping our data in the flattened one in order to continue and to put this data into the final layer that it will be the dense layer that is responsible for the classification, okay, because we have two processes happening in here. So now in terms of the flatten, what happens in the flatten here? Have a look here. The final output that we got from the convolutional, it was 3 by 3 with a depth 128. So this is the cube of data. Yeah? So now from the cube of data, we want to shape it. And if we want to shape it, we want to end up with a vector now of numbers. We are not changing the value itself. It's just changing the structure of the data. From a cube now, we go to like a list of numbers. Okay? And I want to ask you why
Yes,
we
but
have in here
you also each
how
of them,
many
you make them
units we have. And you see that the total number of units that we have is 1,152. Can you tell me why?
3 by 100.
Okay, that's the total data points that we have in here in this cube. Okay, the dimension of the cubes are 3 by 3, 3, and 128. If I multiply all these three numbers, 3 by 3 and 128, I'm going to end up with 1,152 units. So it's the same data that I have, but here they are structured as a cube, and here I'm just having a vector of data. And then what happens? This data now, they will be feeding in the last layer, that is the dense one. Okay? The softmax is going to calculate what? It's going to calculate the value between 0 and 1, and we can use it in order to do the classification and to decide to which class it belongs from 0 to 9, because in total we have 10 classes. Okay? Is that clear? But something that is important, and I want all of you, we can open our calculators in order to understand what happens in terms of the parameters now in each of these layers. So this is the total layers that we have in our network, in the convolutional neural network. The first one, it was the first convolutional layer, okay? And now, the output that we got, it was from 28, due to the loss border, we end up with 26 and 26. We had 32 filters, so 32 different matrix, let's say, these are the dimension, and it will be 26, 26, and 32 in terms of the output shape, what we get from this layer, okay? And now I want you to calculate a bit and think about why the total number of parameters is 320. Something very important to understand here is that we have only parameters in the convolutional layer, and we don't have any parameters in the pooling, okay? Because we are not training, we don't have weights and so on, we are just shrinking. So go there and just select the maximum, or the maximum value, and discard the others. So that's why we are shrinking. We are not doing any learning, okay? And you see that in the two max pooling layer that we have, the total number of parameters, it will be equal to 0, okay? The same happens in the flatten, because in the flatten layer, I'm not doing any processing at all, so I'm just reshaping it, so there is no learning going on. I don't have any parameter to estimate and things like that. So it will be equal to 0, okay? So now let's take one by one, and I want to calculate why you have 320. So
32 filters per 10.
I'm doing, you tell me why we have
32
32
filters
multiplied
per
by
10 classes that we have.
10 classes? No, I don't think that's
32 multiplied by 9. Because each
32
filter,
multiplied by 3 multiplied by 3, okay? Because 3 by 3, okay? That is the kernel size. Multiplied by 32, that is the number of filters. So we end up with 288. So still is not 320.
Okay, perhaps you've done padding. I don't know. No, I don't know.
What does that mean? Why is not 320 again? Do you have an idea? So this is the total parameters. What are the parameters? The parameters are the weights that we have to estimate, if I figure out, So now, you see that in the square 3 by 3 there are 9, Multiplied by in total we have 32 matrix, so it will end up with what? So if I delete, it will be 288, okay? But if you remember when I was explaining yesterday to you the process of how we update the weights and so on, there was a component that I included.
The biases.
What?
The biases.
The bias itself. So now, as we are having 32 filters, for each of the filter we have a bias that we have to estimate as well, to update and so on. So now, plus this 32 bias that we want to include, it will be 320. Is that clear? So I'm talking about values that the model has to update or to estimate, So in total there are 320 in the first layer. Any questions? Did you get confused?
Yeah, why we get the bias 32 because the filters are 32?
Yes. Okay?
Each filter has
Each
one bias.
filter has one bias.
Remember that each
Yeah.
filter applied to an image, there is an operation which is like a linear combination plus the bias.
Plus,
For each filter, we have
yeah.
one bias.
Yeah. So now let's calculate the second one and see why we get 18,000 in order to see how we understand it. So can you calculate the second one, the second convolutional? We have 64 filters. Multiplied by 3, multiplied by 3. What happens? Not by 3. So can you go and we do the other one? So, in the second convolution, so I want to figure out why I have 18,000.
It's the
Can you
same.
calculate it?
64 times 9. Okay.
Did you get it? What?
In each size.
3 multiplied by 3, eh? By 64.
By 32.
But do the calculations. I want you to figure out that 18,000 yourself.
3 times 3
3 times 3,
64
that is, okay?
times 64 times 32 plus 64.
Okay. So now in here, we have 3 multiplied by 3, multiplied by 64, and multiplied by 32 that we had, okay? Now, and we have to add the bias. And the bias that we had here, what is the bias here?
64.
It's 64 because we have 64 filters, yeah? And the total will come up 18,496. I'm not doing the other one, which you yourself you can do it, and it will be around 70 parameters, okay? So now let's discuss a bit in the dense one, why I have 11,000 parameters in the dense one. Do you have an idea? I'm going back now to the flattening here. So, you told me that when we flatten it from the cube and we go to the vector here, what we have? 3 multiplied by 3, these are the dimension of the cube, multiplied by 120 filters that we have, the depth. So it will be 1,152 units that we have in this vector, yeah? And this is something that will go to the dense layer, okay? Now, the dense layer itself, it's fully connected, and that's correct, it's fully connected.
Then
10.
plus 10.
So if you multiply that by 10,
Plus
Plus 10.
for the-
plus 10 for the bias, you will end up with 11,530 parameters, yeah? So now, for this model that I have not fitted yet, I have not deployed yet, but it's just the model that itself that I'm building. I didn't run it at all with data. So the total number of parameters, I have to just sum all the parameters belonging to each layer. Just in this example, it is important to understand that you don't have any learning, training parameters estimation in the max pool layers and also in the flattened one, and it happens in the convolutional layer, okay, and in the dense one as well. If you sum up all these parameters, the total number of parameters it will be around the 104,000 and something, okay, if we sum all of them. Now, do you think that this is a large number of parameters or a tiny one? What do you think?
Kind of model that we want to build.
Usually, we consider it a small number of parameters, let's say, based on the practicing and the real data set that we work, because if we think about large language models, the days and why they are so powerful and so on, is due to the fact that that contains billions of parameters, let's say. But for the task itself, because these are simple images and we want to do just, number recognition in here, so this might be considered a good number of parameters for the task itself. But if we are working for complex or, for example, face detections, feature detections for faces and so on, maybe, not maybe, but this number of parameters, it will be not enough, let's say, in order to work on that. So it depends on the data that you have, on the problem that you have, on the domain that you work on. So if I go in here, so this is something that I want you to leave 1 minute to understand the curve. It's similar to the curve that we looked last week. So we've been talking about,
Before we go to this convergence, can we compare this number of parameters with the number of parameters of the previous model that we used without convolution?
Yesterday.
Huh?
Yesterday we
Yes, yesterday. So how many parameters, if we calculate them, did we use for that model? We had 700 and something multiplied by, I'm not sure.
1,000.
1,000?
Yeah.
Okay. So multiplied by 1,000, multiplied by 1,000, multiplied by 10. I guess it was larger than this one.
Yeah. I
So-
don't remember exactly the numbers, but the idea is yes, it's going to be larger.
Okay,
If
so
you want to achieve
this is
the
more
same-
efficient.
This uses less parameters and gets good performance compared to the yesterday.
And you can also compare the accuracy. I don't know what is the accuracy that you achieved yesterday, but the accuracy here is about 99%.
Okay,
so
so it has
that
a
is
better
where these
accuracy.
convolutional neural networks are powerful, because compared to the model that we used, the neural network that we used yesterday, so we have less parameters, let's say, in terms also on the speed of processing and so on, but you can also achieve a higher accuracy. So this is why they are powerful in terms of using it in image processing. So if we have a look in this now, what we have? In the first one, the blue line is the accuracy, and the orange one is the loss one. So you see that they are the opposite. Let's say once the accuracy will increase, the loss will decrease, and so on. But what is important is we start in the first epoch. We have an accuracy of 0.95, and we reach an accuracy of 0.99. In the last epoch, that it is, in total we have 5 epochs in here. Okay, so it makes sense that epoch by epoch the accuracy will be increased, but something that is relevant and it's very evident in this curve, what is? Yeah, that makes sense, it's logically, because you increase the accuracy, the errors will be decreased, yeah. But something else, what is evident in here?
Well, the first, I want just the first.
The big improvements. Where the big improvements happen?
The second.
So it's like a rapid convergence. So from one epoch to the second. So if you are in the first epoch, the accuracy is 95% in the first pass. And when I say pass epoch, is all the data that we have, the 60,000 images that we are using for training. And after that, in the second epoch, you reach 0.98. So the model is learning now, and the accuracy has been improved. Now, when it comes to the other epochs, from epoch 2 up to epoch 4, this is what we have in the experiment in here. So the accuracy continues to improve, but not a big improvement, let's say. So it's like more tuning happening here. So that's why we say that there is a rapid convergence in the first epochs. Okay? So keep in mind that this is the accuracy that we achieve 90% of the training, the data set that we have. If we now continue and test it, and you have a line of code in here, so what we are doing here, model.evaluate with the test images. So this is another data set, because if you remember at the beginning we load 4 different data sets. This is the test one, and we want to test now on some images that the model, the network has not been looking at. So these are new records now going on into the model. Now I see that the accuracy of testing, it will be 99.1. So it will be a bit decreased, but if we see, can we generalize? Do you see any overfitting issue in this model, let's say? So what do you think? If you compare the accuracy that we achieved, during training and testing, so what you can conclude? We can generalize it, because we don't see any decrease, you know, or a significant decrease in the accuracy of the testing, testing compared to the training and so on, and we can generalize that this is a good model in terms of image recognition or digit recognition and so on. Now, this is the, I don't know, we are running out of time most probably.
It's okay.
Yeah, but it's okay, let's finish, there are 2 more slides. So now, the what if scenario. So think about now that if you run the first code where you have convolutional, max pool, convolutional, flatten and dense, so this is the architecture. So now if you go and delete remove the 2 lines of code, so you are now having a convolutional neural network, but without having in place the max pooling. So delete these 2 lines of code and you run it again. What it will change?
The number of parameters.
So what it will happen now?
It will increase the number of parameters.
So what we are going in depth because I'm not changing convolutional layers at all, so I'm keeping the same number of filters. It will be 32, it will be 64 and 128. But what happens? I'm not shrinking the data with the max pool. There will be a bit of shrinking that comes due to the loss border from one convolutional layer to another. But there will not be the dramatic or the significant shrinking that comes due to the max pool. And in the first one, this is what we ran and we explained till now. 26 by 26, after that 13 by 13, okay? 11, 11, 5, 5, and we end up 3, 3, okay? When it comes to the other one where we do not have pooling at all, we remove the pooling. So it will be 26 and 26 by 26, yeah? After that, the convolutional is going to shrink a bit due to the loss of the border from 26 to 24. And after that, again, it will happen a shrink from 24 to 22. And we'll end up having 22. Now, it's not about, when we talk about or compare with pooling and with no pooling, what it will be the main challenge, the main issue? The dimension itself, what the constraints brings. It's about what? What?
Make the algorithm more complex.
It's about the total number of parameters. It's all about parameters. If we shrink them, we are just having less parameters. That is the process of shrinking. So if with the first one, and we consider it as a champion one with pooling, so the total number of parameters that we calculated ourselves step by step for each layer, we ended up with having around 104,000. Okay? If we remove pooling at all, and now we recalculate again the parameters and so on, so we'll end up with having a total number of parameters of around 7 times more in terms of the number of parameters. Okay? So this is what happens. And also, if you have more parameters, it means that, because I skipped this one, so having 11 k parameters, using now the max pooling, and if we don't use the max pooling, we'll end up about having 700,000 parameters, which you see how big it will be that vector that we want to pass through the dense layer in order to do that process of classification itself. And this comes with a high cost. Okay? That is the reason that we consider, I think it's here, the hero. I told you at the beginning that max pooling layer, it might be considered as a hero in terms of reducing the complexity here, but keeping a higher accuracy in terms of the image. And I think this is the last for today. So what we have, at the first, when we start with 32 filters, what we do? We try to figure some simple patterns from the input data that we have, our data, let's say. And after that, going to the next one, when we increase the number of filters, we go to 64 and so on. We combine now, this will be the input now. So these simple patterns that we have identified from the first convolutional layer, it will be an input going to the second convolutional layer, where we have been increasing the total number of filters. These patterns will be combined in order to create and to figure out more complex here now. By the downsampling, we are not interested anymore to know exactly where the pixels are located and how are located, but we want to identify the object itself, and what will end up with a global context in the final layer. So we are in a point that we have identified the main object. Okay, so that's all for this one, and after the break we'll continue with there is a quiz, and we have some exercises planned for the day.